Oh, by the way, before we get started today, let me plug the Math Club. Today is Freeman Slaughter. By the way, that's one of the coolest things I've
I
ever
saw
heard.
that. I screenshot that email and sent that to so many people. I thought that was the coolest thing I've ever.
He's going to be doing he's going to talk about the mathematics of chess. So, you know, I can see that being appealing on many levels. So I encourage y'all to be there. You should get an email with the Zoom link. If not, let me know. Other than that, do y'all have any questions before we get rolling?
I wanted to ask about, I think it was number 6. I know I came to ops hours, but why? So when it's order, when a redevelopment's order 2, it means it's abelian. So why
Yeah,
is that?
right.
Why is that necessarily bad? Like, what is wrong with that?
You can show inductively by the number of generators that if you have a group that has all elements order 2, it has to have order 2 to the end. Right?
Oh,
And there's another way you can think about it, and I know you might think about it this way because you had 85-20, but you can think any group that has all elements order 2 is a vector space over V2. And so there is a direct sum of a finite number of copies of C2, and therefore has to have 2 D elements, right? And that can't happen if the order group's 2P, right? Where P is an odd prime. Okay, so the last thing I left you with is this really cool theorem about the direct product. And so in lieu of writing the entire theorem again, repeating it, let me just kind of draw a diagram. Remember, the direct product is just sort of nets, right? Sort of generalized sequences, GI, where each coordinate comes out of the I one of these. This is a projection map onto the K coordinate, if you will, right? Where you just read the K coordinate. Your situation is you have a family of homomorphisms from H into each of these GKs. Remember, these can always exist because if nothing else, the Kth one of these might be just the 0 homomorphism, or the trivial takes everything the identity. Direct product means that you can lift this information. So you got all this information, H goes into each one of these little sort of factors that make this up. You can take these and lift it to a sort of grandpappy, if you will, homomorphism from here to here that makes this diagram commute. So basically, the spirit of all these homomorphisms is captured. So the results of this is there's a unique capital phi that makes this diagram commute. And we'll show uniqueness. And this determines the direct product uniquely up to isomorphism. So we are going to start to prove this by basically just saying this. Okay, help me out here. Remember, what's the big theme in math? If it ain't easy, don't do it. So I want to start with something here in H. And I want to somehow use this information to make us spit out some sequence, net over here. And of course, this is the tool I want to use. What should the ith element of this be? Well, I need my ith element to be in GI, right? So why not use little phi? Fantastic. Everybody agree that this goes where I claim it goes, right? Because what this is supposed to be, this is supposed to be a net, and the ith coordinate is in GI, and that's exactly what we've got. This is certainly well defined because each little phi is well defined. Notice, of course, And just by the definition of the way we multiply these nets. So, okay, good enough. I've got a homomorphism. Also note. If you have any K in the index set, when I do C, what is this? Okay. And ask yourself this, so what does pi k do? Well, pi k reads this net and it just bars out the k coordinates. So this should be which is exactly what I want. So when I do capital P and projection, okay, so I've got existence, I've got the diagram commutes. Now all I need is uniqueness. And then of course I'm going to show that it's unique occurrence points. So continuing, now I want to show this is I needed this to be a unique homomorphism. So let's suppose pitchfork any homomorphism product such that the pitchfork apple and pi k basically we have to show that this does the same thing that P does, or the same thing apple. So notice the pitchfork of any age should be I don't know much, but pitchfork of age has to be some net that lives in the direct product. And when I do pi k of pitchfork h, this should be correct what it is. This is xk, which should be therefore every xk is pkh. And so by definition, pitchfork is exactly the capital P. Okay, so here's where we are. Homomorphism exists. Homomorphism is unique, makes the diagram commute. Now, The interesting part here is we're going to show that the direct product is the unique solution to this universal mapping problem. So let's suppose oh, right. Now suppose, well, direct product. We suppose that H is another solution to this universal mapping problem. So let me be more specific. Yeah, whenever I write O, that's what I mean, universal mapping problem. Let me be more specific. So H is approved. Equipped with a collection of functions HI from H to GI. At the more interesting. So basically what I'm doing is I suppose that I have another group H. This is just like a direct product that is equipped with something like our projections, right? These epimorphisms. We'll see what we can get out of this. And this is really, I think when you're done with this, you're going to think that I kind of cheated you a little bit and got away with something kind of shady. So we have the following. My family class that I have here, HI. And so going this way, same as going that way. We have this because we've already proved that this is a solution to this universal mapping problem. That is, if I have a direct product, and I've got this H, this new H that I built, but this H nonetheless, then I can lift this homomorphism, right? But also, H is a solution to first here. So we have this. And actually, not bad. Okay. And this map is, of course, my H vector. think we can all agree that I have these projections on the GK because that's what this does. By hypothesis, I have these homomorphisms, HI, well, specific ones HK here, right? And so if this is a solution to the inverse mathematical, we also do this. We call this. Everybody agree with that? Now, let's kind of glue this together. Let me turn this into a giant diagram. Here's the most recent one we did. It's also like this. From the first triangle. Let's go. Got this. Everybody with us so far? So basically, I sort of stood this one up straight and glued it together. Everybody okay with that? Now, focus on the outer triangle. Forget about the middle for a moment. Forget about this. This is just a stop on the train station. Let's forget about it. Notice there is a homomorphism from the direct product into GK and a homomorphism from the direct product into GK. So there should be a giant, very large homomorphism from here to here. Everybody agree? Because this is a solution to the universal mapping problem. So you should be able to make this giant triangle, right? Here, here. Everybody agree? Did anybody name a solution to that? What is a function? What is a big yellow arrow function that will make this diagram commute? Can you identify it? What identity function? Does everybody agree with that? That works. But what do we know? The solution is unique. So, what do we get? We get the identity function on this is equal to this. Now, I could have actually put the triangles together using this as the middle spline. Right? Everybody agree with that? So I didn't do this, but I could have, instead of gluing the triangles together with the HKs, I could have done with the pi k's here. And I also get one H so these are two group homomorphisms that compose the identity in both directions. So and that does. So H, two solution of the time is isomorphic direct product. Questions on that? That's kind of cool, right? Because what we got here is the identity works, uniqueness gets it's the only thing. So these two compose the identity function, which of course immediately gives, this is on to and this is 1-to-1. When you do the triangles the other way with the package in the middle and the HK flanking, then you get in the other order being the identity on H. Okay, any questions? Okay, so let me follow up. So, theorem 345. You know, I actually forgot to say something about the homework, which I always like to do, so I'll do that at the end of class, actually. If is a family of groups, then number one, or A, the coproduct of GI. Don't forget, this is just the subgroup of the product where almost all entries are the identity. The normal subgroup, direct product. B, for all K and I, the function I O to K from GK into coproduct. Let me tell you how this works. This is, I think, it's easier to see the projection than this. My input is a little piece of K. Let's see, its output should be a sequence. Or a net, again, I should say. Any, yes,
Is this an I or
it is my pathetic attempt at an iota, right? It's sort of like a little
no?
Greek
So it's not
thing.
like the identity I.
No, but it's, you're gonna see it's sort of why they might use this. So if you look at iota K of G of K, I've got to input a single element and get sort of a net out of it. Any ideas on what here? So help me out here. There. XI. But now I'm going to tell you what the XI is. Any ideas? Do I show my hand doing the LaTeX cases thing?
Almost zero spot on the page.
Right. This should be GK. So that means whatever this is, shove it into the appropriate coordinate, right? And what if it's not? What if you have a different coordinate? Just make that the identity of GI. So the identity everywhere except in the coordinate that you want to get. And number C, for all K in the index set, if you look at the image, iota K of GK, this is normal in the direct product. Yes.
What's the conclusion for part B? So we have a function like that, and
Oh, I'm sorry, I didn't even write the conclusion, did I? Is a monomorphism of groups. Thank you. So this is a homomorphism of groups that's 1-to-1. Here is a theorem that should look very much like the theorem that we proved, universal mapping problem theorem for direct products. This one's going to be for co-products. And I want you to notice something really cool about this theorem. Let AI be a family. Okay, yeah, I'm going to do this for abelian groups here, and I'll say something about that in a moment. Yeah, so we're going to specialize to the abelian group for this thing. We're going to call it direct sum. If E is an abelian group, and here I'm going to do these pitchforks from AI to D. Homomorphisms from AI, well, each pitchfork guys from AI to B. There exists a unique, from that's this is exactly the same. I may have said something about this earlier, but this direct sum, this is the same thing as the co-product, except this notation is used when you have abelian groups involved. There exists a unique homomorphism from the direct sum or the co-product of these abelian groups, such that when you do I and K in capital pitchfork, it's pitchfork. So A. And this property determines the direct sum of A and I. So this theorem is I mean, it's basically the same structure as the previous theorem, but I want you to notice a couple of key differences here. Let me set up the diagram first. I want to draw a picture just like I did before. So we have, excuse me. You have for each one of these AKs, you have a homomorphism from AK and B. You also have I over K. Right? And so what this theorem says, excuse me, is if I give you this family of homomorphisms, and again, there's always some homomorphisms from AK to B. And we have these iota inclusion things that we built over here. Then basically, the maps in this direction allow you to lift to a sort of master homomorphism in the direct sum. Now, notice this diagram is exactly like the direct product one, doesn't it? Except all the arrows are reversed. Right, everything's reversed. In the direct product, the arrow went this way, that way. This is a dual structure. So any of you that are interested in things like categories, this is a dual construction. Actually, from my research point of view, this one's the more important theorem. This one's probably the more important direct product. Of course, you get both of these theorems if your index set is finite, don't you? Right? Because there's no distinction there. But this one leads to some important things. So, for example, you can use this to show that a big theorem in community algebra, for example, is every module is a homomorphic unit. 3 modules that solves direct. So basically, you can project anything to be projected onto by the direct sum, which is kind of cool. Now, why did I restrict to abelian groups? Well, I'm not going to do this entire proof. In fact, the exercise about showing this property determines this uniquely of isomorphism is almost exactly like that thing where you put the 2 triangles together differently, and it's the same sort of thing. But the difference is I want to show you how the math works. So I'm going to do a partial proof. Okay, so I'm going to start out the same way. This is going to be interesting. I've got to get a homomorphism from, I'm going to start by building what I want this capital to be. Given this fact that I have this data here, I have homomorphism from each separate bit here. So say AI sum. Again, we've got one of these super nets here. Now I do know that. See, I'm going to talk about abelian groups. So I'm going to talk about the structure of all these groups additively. So I'm going to talk about additive structure here. So in this net here, almost everything should be zero. Right? I am going to define to be what? Anybody want to take a stab at that? I think this one's a little bit more tricky. I mean, it's not super tricky what I'm writing it down, but there's a detail. What I'm going to do is I'm going to take each entry and I'm going to apply AI. Right? I mean, that's the information I've got. I know that each AI has a PI, and I can. So each one of these little things can be. Everybody agree? And then I'm going to sum up the index. Now, the people in analysis, and I know there's big fans of you out there, this should probably set off a big fat warning light. What could be wrong here? That's correct, right? I mean, it's hard enough to make things converge to reals, right? I've got some stupid, group here. What the heck's going on here? But the infinite sum business is not an issue. Why? Well, that's right. All but finite and many AI are zero. So this is a class. it's sort of an infinite sum, but infinitely many of these things are zero. And of course, PI of zero is zero. And so you can construe this as primes. From here, check it's a homomorphism. And when you check it's a homomorphism, you will probably see why I want this to be. Besides that, the proof is essentially the same. Okay, any questions? Any questions? Let me give you a theorem. This is stated maybe a little bit more generality than you've seen it before, but you might have seen it. And here I'm going to go back to co-product here. I'm going to allow this to be non-abelian. Let Ni normal G. I want it to have a couple of properties here. First of all, I want G to be generated by the union of these NIs. Okay, so here's the situation. I have a collection of normal subgroups. I've just got a collection of normal subgroups of G, non-equal say, and I want G to be generated by the union of these normal subgroups. So if I take a shovel and throw all these normal subgroups into a thing, then all the words that they can make get all of G. Number two, for all K in this index set, if I look at NK intersected with what's generated by NI for I K, this is the identity. Okay, so here's kind of the deal. When I take NK and I look at everything generated by all the normal subgroups that aren't K, the overlap here is only the identity. Oh, that's all I need. Then Q is isomorphic. Actually, to the whole product of NI. Let me give you a simple example. Okay, so I want to look at I will assume it's not counted here. I want to look at a couple of subgroups of this. Let's look at subgroup generated by two bars, right? 0, 2, 4, 6, 8. So if you look at this group, what's generated by 0, 3, 6, 12, 15, 21, and 5 bar. Yes. Yeah, I'm on that, because actually, I've got subgroups and cosets turned around here. Let me fix this. What I want is subgroup 1, 2. Let's look at 1, 2, 3, 5. So let's look at this. Okay, that's a subgroup. There we go. I want one of order 3. So how about 10 more? And I want 1, 5, 6 bar. Okay, everybody agreed that these 3 are subgroups. Notice that, and this is, we'll say this is M1. I first claim that the group generated by M1 union M2 union M3 equals all of these are. Anybody justify that? It might be easier to know if it's C30.
15 minus 10. And then you subtract it from 6, then you get 1.
Yeah, that's one way to do it, right? Notice that if I have all these elements, so I've got a grand total of 2, 5, 10 elements, right? Notice that when I've got all 10 of these, well, actually there's less, it's 0 should be there, there's some others, but well, actually only 0. Notice that if I have all these elements thrown together, for example, 15 plus 6 is 21, take away 20 is 1. So, and once I've got the 1 in there, then I've got it. The second condition is, if you look at, for example, M1 intersect the group generated by M2 union M3. Well, what is the group generated by N2 union N3? Well, anybody want to guess what it is? What is the group generated by N2 and N3? It's a subgroup generated by 2 bar, right? Let me point out the 2 bars in here because you've got 12 minus 10, so that's in there. And notice that it's pretty clear, isn't it, that every coset when you generate these 2 should be all even, right? Right. And so this intersection is only 0, which is what we need here. For example, N2 intersect N1 union M3. Well, what about M1 and 3? Any ideas what we get here? I bet it's group generated by 3. Right? Because, for example, 15 minus 12 is 3. And notice everything in both of these has multiple 3. Notice we're getting the first groups I was writing down when I made a mistake, and that's because I was thinking of modular versus subgroup. And the same for the other one. So in other words, Z30 is isomorphic, but N1 directs N2 directs N3. It's actually co-product in general, but in this case, we don't need to distinguish, which is actually isomorphic to N1 is isomorphic to N2. 3. The cool thing about this theorem is it even works if you've got an infinite collection of subgroups. Okay, so let me start to prove this. Yeah, this is important.
Still want to talk about that.
I did, yeah. Proof. So note if this is the hand of proof, first note if A is in J and I and B is in J, combine J different, then look at that little commutator here. Notice that this is in Ni, and so it's this. So this is in Ni. Agree? And this is in NJ, as is this. It's NJ. And notice this is weaker than this, so this is the identity. Because the intersection of any two different ones is going to be the same. So what you get is A inverse, B inverse, AB is 1. So you get AB. So the upshot is if you have two elements, one that lives in one of these normal subgroups, and the other that lives in a different one, then they commute with each other. Okay. So I think this is probably a good place for me to quit the lecture. We'll pick this up next time. But I did want to say a quick couple of words about the homework. And by the way, you probably want to look over the proof of this for next time. Don't like that. Go through it pretty quickly. Homework here. So your next assignment here. So you all in the home audience can see this, correct? Okay, good. I'll see if a lot of people can see. Okay, so the first problem, I like this problem. I like examples. Suppose that K and H are groups with the property that they're group monomorphism. So I mean a homomorphism from H to K that's 1-to-1. And a homomorphism from K to H is 1-to-1. Now, this is a big thing from set theory that you may recall. You all remember this famous theorem that if you have two sets, X and Y, if there's a one-to-one map from X to Y and a one-to-one map from Y to X, then the cardinalities are the same. Well, the cardinalities of these two groups are the same. You got homomorphisms in both directions that are one-to-one. Does that mean that they're isomorphic? Prove this or give a counter example. By the way, the answer is yes, it's a finite group. So if there is a counter example, that's big in a certain sense. Number two, let G be a cyclic group. Show that G can be decomposed as the direct sum of H and K, with H and K non-trivial, if and only if G is finite and is not a prime power. So this is actually kind of an important thing. So if you have Z mod N, you can always pull it apart as long as N is not prime power. And this also says that you can never pull Z apart into a direct sum. Number three, let G be abelian with subgroups H and K. Show that G is the isomorphic to the direct sum of H and K, if and only if there exists these crazy maps. The pi's project from G out onto H and K respectively, and the iotas go in. When you do pi 1, iota 1, or I'm sorry, when you do iota 1, pi 1, you get the identity on H. When you do iota 2, pi 2, you get the identity on K. If you do pi 1, if you do iota 2 and then pi 1, if you go all the way across, you get 0, go all the way across the other way, you get 0. And the sum, iota 1, pi 1, iota 2, pi 2 is the identity on G. Here I'm writing my functions additively, right? Or I'm writing my elements through additively. So I mean the sum of the maps is just the pointwise sum. And finally, number four, suppose G is a group and consider the automorphism group G. Show that H across K is a subgroup of H across K. I'm a little sloppy with that notation. That is, show the left side to be identified with the subgroup. So show that there's a one-to-one function here, the one-to-one homomorphism. Show that if the order of G is greater than 2, then there's always a non-trivial automorphism. So if you have a group of order 2 or 1, the only automorphism is trivial. But if you've got more than 2 elements, there always has to be a non-trivial automorphism. Show that the inner automorphisms of G or G mod ZG. This one actually is too difficult. The inner automorphism is defined in the first homework. And finally, find these 2 automorphism groups. This one's familiar, and this one you can probably think of as matrices. In fact, one way to think about this, if you like, is via linear algebra. That's one way a number to do it. Anyway, hopefully those will be kind of fun. Don't forget your homework's due today. And I encourage y'all to be at the math club if you can. And also, how many of you are first years? Okay, this is First Friday, and historically, I can tell you that if you've got a card up here, if you're here at the start of the parade, you're going to be here till the end of the parade. So anyway, that's a heads up on that. Okay, other than that, y'all have a good weekend, and I will see you on Monday.
Wait, what about parking?
When's the parade start?
I think it starts at 6, but I think it's warmed up about 5. And so it's, I mean, if you're parked up here, it's fine. But I mean, if you're near where the parade is, this probably affects me more than you because I parked in a cycle place. But I think that, you know, if you're in this place between Long and Martin, then you're kind of stuck. If you're here at the front of the parade.
Our stuff here.
I don't know what a parade.
Yeah,